All right, welcome back, everybody. Today we're talking about flux and surface integrals. We're actually going to go through sections 12.3 and 12.4 today because the section after that, 13.1, is particularly long. So I think I'll spend 2 days on that, or 2 videos on that. And then we'll just shove 12.3 and 12.4 together today to try to make up for that. And so we've got kind of two ideas going on here: flux and surface integrals. Surface integrals is just kind of a more generic term for what's happening. This means we are going to integrate over a surface instead of a curve or a 3D region, which is really like a volume. So we're thinking about integrating over some sort of 2D region that's possibly curved in 2 dimensions. So think about like the surface of the Earth or surface of a Pringle chip. Any object we grab, right, in 3 dimensions, it has a 2-dimensional surface. So we're going to compute values via integration over these surfaces. And flux is a specific form of this. So flux is a specific surface integral which measures a vector field through the surface. So in some sense, we're asking the question, given some, and I'll make my life easy and just draw a plane. So there's some vertical plane. You can imagine maybe we have a vector field that looks like this. Okay, we're in the sense of a flux. Flux is like measuring just the vector. We're adding up every single vector, which is perpendicular to the surface we care about, and we'll specify that a little bit more clearly later. But that's the idea for today. And if we look at the following figure here, we have a surface. We're going to call our surfaces in this class sigma, right? Greek capital S, more or less. So our surface will be sigma. And we have this notion of normal vectors to surfaces, which you'll recall from the previous section. The normal vector for a surface is calculated by the gradient of f at that point. And it's normalized. x1, y1, z1. And in particular, where f of x, y, z equals some constant, this is a level surface which describes sigma. Okay, so if we have some level surface, then we can compute the normal by calculating the gradient of f and normalizing it. So there's 2 examples of some normals of this particular surface. And if we want to, maybe let's draw a vector field on here. I'm going to start to get a little bit more specific. Suppose I have a vector field. For some reason, it only points in this direction. Okay, so there's my vector field V. I might want to ask the question, how much of this vector field passes through the surface? Passes through sigma. So how much passes through? So when you pass parallel, you don't pass through. Parallel is not through. For somewhat obvious reasons. If I'm walking along the surface of the Earth, I'm not passing through the surface of the Earth. I would have to dig a hole or jump up from a hole to actually pass through the surface. And if we look over here, perpendicular is passing through. Okay, so we want to think about some way, how can we measure the total amount of perpendicular vectors of some given vector field? And the easiest way to measure that is with a dot product. All right, so we're going to take our dot product and we're going to take the dot with the normal. And just don't forget that the normal can be calculated with the gradient that's normalized, the gradient of the level surface and then being normalized. So vector field dot, the normal, will give me the total amount passing through at any given point. This is, maybe I'll write that down. The amount, if I can spell, passing through at the specific point, x, y, z. And then if we want the total, So if we want the total amount passing through over some region of x, y, z's, that's of course integrating, right? Integrating is a fancy word for sum. I'm going to sum over every single point x, y, z within the region of my surface sigma, and I'm going to take the dot product. And this is what we call our flux integral. So if you remember one thing from the first half of today's lecture, it's this definition for the flux integral, v dot n over sigma. All right, so there we've provided a few extra different vector field, and so you can see that, for example, these are going to provide more of a passing through than maybe over here. If the vector field v is pointing exactly parallel to my surface, there's not really a notion of passing through there. Okay, so let's actually calculate it. Total flux through a plane. So we're going to look at the following situation where we have a vector field xyz, nice and relatively trivial vector field, and then I've got a planar surface, and by planar that just means it's a surface which looks like a plane, given by the region in x 0 to 1, the region in y 2 to 3, and then z equals 5. So how do I want to consider this as a plane? This is actually my plane equation. I'll say the equality is the plane equation. The inequalities, or the regions describe my integration bounds. Okay, so I've got some bounds 0 to 1 and 2 to 3 in x and y, which describe kind of a rectangular region of the plane equation, plane which is described by z equals 5. And so from that, I can say since the level surface, which we think about as f of x, y, z equals some constant, that's a really bad z. So x, y, z equals a constant is, in this case, z equals 5. So that's the level surface. I calculate the gradient of z, which happens to be the vector 0, 0, 1, is my normal. Notice that vector is already normalized in this case, so I don't need to divide by the magnitude. And that's where now that's why this little example has included for us that the normal is 0, 0, 1. Okay, so now I have v and I have a normal. I'm going to take a dot product. V dot normal happens to be just z, right? I take that times that, I get 0, that times that, I get 0, and that times that, I get z. So I add all three of those up and I get z as my dot product. So if I translate this is equal to the integral over the region. The region is in x and y. In the x direction, my region goes from 0 to 1. In the y direction, my region goes from 2 to 3. V dot n, we had decided already, was z. Now, in particular, what is z within the region? Keep that in mind, z is just equal to 5. So that's where the example is finding z equals 5 here, dx, dy. And now I'm just going to compute. So the inside integral, this is jumping back now to integrals of scalar fields. The inside integral gives me just 5. Now the outside integral is going to give me 5 times 3 minus 2, which is still going to be 5. Okay, so the total flux here is 5. And that describes the total amount of vectors which are passing through the surface. Okay, we'll cover some more complicated ones in class, but now we're moving on to area forms and integration. Area forms in the sense of, instead of calculating, this should be called surface area. So think about area as surface area, forms and integrations. So instead of calculating like arc length back when we did with curves, we're now calculating surface area. So it is kind of the higher dimensional version of an arc length, and that's going to be a surface area. So really we're thinking about surface areas within this section, but you can also you can compute a few other things which are related to surface areas, right? We could assign each point on the surface a number, and then we would add all of those numbers up. So we're going to get something. There are some cases where you could get something like quantities that are non-surface area quantities, but the surface area is the simplest one, right? So let's just look at the first example really quick. So basically what we want to think here is that we're just integrating over a surface, right? We're integrating a surface over itself. That's what this describes. Integrate a surface over itself to find its area. But we have to kind of describe what does this actually mean, d sigma. That's kind of the tricky thing here, is to really understand what d sigma should be. Okay, so I'm just going to write it out for you, what d sigma should actually be, and then we'll see maybe why that's the case. So given a graph, so x, y, f of x, y. So this is our three-dimensional graph. You can think of f of x, y as, z, but it's a function of x and y. What we call surface differential, d sigma, is just like the one higher analog to our surface area differential. So we're going to get partial f partial x squared plus partial f partial y squared plus 1. So if you'll recall from arc lengths, it basically, we only had one of these derivatives squared plus 1 in arc length formulas. This was back in the section where we introduced curves, I believe integrals of over curves. But now when we have really two directions that we have the ability to move in, we're basically saying, okay, I'm going to move in the x direction by an infinitesimal amount. I'm going to move in the y direction by an infinitesimal amount. And the one here basically says that the z direction remains constant. It's like partial f partial z, which if f of xy is z, then it's partial z, and so you get 1 squared there. So traditionally you would just have, the change in x, the change in y, and the change in z. You square all of those, add them together, and take the root, and that'll give you like your infinitesimal change in area. But because of f is exactly z, then partial z is just 1, and then you take the square root. And I guess maybe I should write it's that, but then it's dx dy. Okay, so this whole thing now is our d sigma that we want to keep in mind for this entire section. So every time I see d sigma in an integral, that's what I'm going to be thinking. Okay, so let's consider this example. This is going to be the area of the unit disk, and it's somewhat of a trivial example, but we should go through it anyway. So thinking about the disk as a subset of R3 now, all of these surface integrals exist as a subset of R3. So the unit disk, which is just x squared plus y squared is less than 1, it kind of looks like this. In R3, it's supposed to be, this is your xy plane, and it just sits inside of there like that, which means the z value is constantly 0. So really our graph here is x, y, f of x, y, but f of x, y, which is our z value, is in fact 0. So it's x, y, 0. Which means that this whole d sigma, which happens to be root partial f partial x squared plus partial f partial y squared plus 1, since f is 0, both of its partials are 0, and we just get 1 dx dy. And so our life gets really easy. We just have to make sure that we compute sigma correctly over here, like the region itself, but then it's simply against dx and dy. So how can we find the region sigma itself in terms of x and y? It's not too hard. Let me clear the screen really quick. It's not too hard. If I look at this, that's the region I'm looking over. Let's just solve for y. And to do that, all I'm going to do is I'm going to pull x to the right-hand side to get y squared is less than or equal to 1 minus x squared, or in other terms, y is less than or equal to plus or minus 1 root 1 minus x squared. Which means when I'm integrating, if I do my double integral of 1 dy dx, then the region which y is integrating over goes from negative 1 minus x squared, root 1 minus x squared, to positive root 1 minus x squared. And then, in particular, what is the minimum value of x? Let's just say x minimum, x maximum. The minimum value x can achieve on the circle is negative 1, and the maximum value x can achieve on the circle is positive 1. So rather than x min and x max, I'm going to replace that with -1, and +1 for x. So then this computes as, if I compute the integral in y, just the inside integral in y, and evaluate at the two bounds, this computes as 2 root 1 minus x squared dx, and then I'm computing x from -1 to 1. And this is the sort of integral that you may or may not have actually learned how to do. Traditionally, we would use what's called trigonometric substitution for this integral. So I'll just say that here. If you haven't learned it, that's fine. But this would be trigonometric substitution. And that would give us a solution of, I suppose, pi? Yeah, that would give us pi. So trigonometric substitution here would give us pi as an answer. All right, so I will clear that then. Let's scroll down and see that they arrived at the same solution. They did things in y instead of x. Totally fine. You can either solve, you could solve the circle equation for x, or you could solve it for y. You'd get the same answer. So you can see this final integral is the same one we had before. It's just every y has been replaced with x, and that's fine so long as we're symmetric like we are in this case. Okay, scrolling down a little bit more. There's some calculations here, but as long as you remember what I told you about d sigma, none of this is going to matter much. So let's jump down here to the differential of the scalar field. And in particular, we like to use the word total differential. So a lot of people will refer to this as the total differential of a scalar field f. And all we want to think about, if somebody references that, it's partials dx, partial in the x direction dx, partial in the y direction dy, partial in the z direction dz. Now, I don't know why the book has included this particularly right now. It's not that important. It's a little bit important maybe for the derivation of the d sigma I gave you earlier, but aside from that, it's not too terribly important in this section. But it's a nice definition to know because people might refer to it in the future. Scroll down a little bit more. Once again, this is just the derivation of d sigma, okay? So come over here, and I'll show you that, yeah, the book also spends 2 pages deriving that d sigma that I showed you right away. And of course, it's important to derive these things in math, but you're all chemistry majors here, so I'm not worried about you necessarily knowing how to derive this. But that's the exact same formula I gave you from the beginning. Make sure you memorize this, okay? This is probably the piece I want you to memorize today. Okay, and this is specifically for the graph xy. In this case, they've given it a g instead of an f, but sigma for that surface. That's something that you're just going to want to know. So let's actually compute the next one, the surface area for the northern hemisphere, right? So let's think about, we have a globe, we're going to chop it in half, and we want to calculate the area of the top half of that globe. And it's pretty easy to consider the graph xy root 1 minus x squared minus y squared. Where does maybe this root come from? Comes from x squared plus y squared plus z squared equals 1. That's my unit sphere, or my sphere in 3 dimensions with radius 1. Solve for z. We get z equals root 1 minus x squared minus y squared. And of course, then if I'm writing my graph in terms of x, y, and z, there's my z. Right? So this z and that z are the same. So that's where that comes from. And then if we want to compute sigma, d sigma here, then we need the partial derivative of this with respect to x and then with respect to y. If I take it with respect to x, I'm not going to waste your time here, but I know some of you might be unsure about it. You get negative x divided by 1 minus x squared minus y squared. And if I take the derivative with respect to y, I get negative y over root 1 minus x squared minus y squared. You can verify those yourself if you want. Plus 1, that's my d sigma that I'm going to use. And it's pretty clear that this will simplify a little bit, but we'll scroll down and see how it simplifies. It simplifies as just 1 over 1 minus x squared minus y squared. Okay, so that's the first thing we always have to do when we're calculating surface areas, is we have to calculate d sigma, and ideally we're going to simplify that. So here we go, we have root 1 over 1 minus x squared minus y squared dx dy. Now let's think about the question before we set up this double integral over sigma of root 1 over 1 minus x squared minus y squared. dx dy, we have to be clever about what does this mean? What is the region that we're actually graphing over? And it shouldn't be too much of a surprise to you all that sigma is the same as for the unit circle before. Because what is the x and how do the x's and y's change over the northern hemisphere? Well, the x's and y's, we still have this ability for x to go from plus or minus 1 minus y squared, and we have the ability for y to go from 1 to negative 1, right? So replace that sigma there with negative root 1 minus y squared, positive root 1 minus y squared, replace the second one with negative 1 to 1. So this is now the full integral that we would end up calculating if we wanted to calculate this this form, the surface area. And I'll scroll down and we'll see something special that the author writes here. Okay, so yes, there's the integral that we just saw. Integral from negative 1 to 1, negative root 1 minus y squared to root 1 minus y squared, and then we have d sigma in here. And it turns out it's going to be 2 pi, which is just what we'd expect because we can use our classical definition for the surface area of a sphere as 4 pi r squared equals surface area of sphere. And if r is equal to 1 and we're only calculating half the surface area, then we better end up with 2 pi. But, you know, I'm sure you're all terrified of actually computing this. I would be too. And then we'll look at the next remark here because of that. Okay, it says the above integral is rather hard to compute in Cartesian coordinates, and this is something special that we're going to start talking about now. We're going to choose a different way of computing the integral to simplify this problem. This is really setting us up for chapter 13, or the next chapter that we're getting to in this book. So that's what this is setting us up for here. Surface integrals can be nasty if we represent a spherical object in a square world. That's the way we can think about Cartesian coordinates, is say we're placing a spherical object in a square world, and that's not very easy to compute. Anyway, let's just take it for granted that after setting this up, we can compute it and get 2 pi. The setup is the important part here. We can talk about setups more in class. I'm still not going to worry about that because that's still just more derivation. Then let's talk about the flux. Okay, we're jumping back one section. So let's talk about the flux of a vector field through the northern hemisphere. So if we'll recall from the previous section, the flux was the surface integral, except now instead of just putting d sigma into my integral, I put a little bit of extra work in and I go vector field dot a normal d sigma. Okay, so the d sigma is the same as for flux. This has not changed. That has not changed. But now I'm throwing this inside. So upon throwing this inside, I need to calculate the 2. So if I calculate the normal, let's recall how to calculate n. It's the gradient of f divided by the magnitude of the gradient of f, where the surface is f of x, y, z equals c. Okay, so in this case, for a northern hemisphere, the surface is x squared plus y squared plus z squared equals c, and I can calculate the gradient to the left-hand side as 2x, 2y, 2z. And thankfully, we have a notion of what z is. So I'm going to go and shove z in there as 2x, 2y, 2 root 1 minus x squared minus y squared. And that is now the gradient of f. And we would have to normalize that. Let's see where the book heads when it normalizes that. Book makes your life easy because it keeps the normal vector to the unit sphere just as x, y, z, and we're going to see why this makes it easy. Because if we jump down to the flux integral, there's v, and there's n, and if we multiply, if we take the dot product of v and n, we end up with the following. So it's v dot n, we end up with the following, but because we're on the sphere, that's equal to 1. And so we end up with precisely the same integral we had before, minus our typos here where we've forgotten negative 1 to 1. So in fact, this is the same integral we had before, and we calculated before that this was equal to 2 pi. So that's the flux in this specific case. Anyway, I know this a lot of this stuff is actually very tricky, We're going to be working really hard on this in class because I'm sure there were a lot of things in this lecture that didn't exactly make sense to you right now. But just stick with me. We can talk about it a lot in class. I'll make sure to not assign too many homework problems so that we can really feel very thorough on this stuff. All right, that's all I have. Thank you very much. Bye.